Bismillahirrahmanirrahim. Assalamu alaikum, students. Today we will continue with the last two lectures in which we have been discussing an example. Let me write the example. We are discussing the example of a simple sipping half solid. So our example is an assembly of particles with two states which is also called sipping half solid. Let me write here sipping half solid. So today's lecture is in continuation with previous two lectures. Let me write here continued with previous two lectures. In the last lecture, I lost my internet connection. I couldn't complete this example. Today, I hope I would be able to complete this example. So let me refresh your memory. Which example is under consideration? We have an assembly of particles with two states. So we have n localized, capital N is the number of particles. They are localized, weakly interacting particles in which there are just two one particle states. One state we have labeled with J is equal to 0, and another state we have labeled with J is equal to 1. In the first state, J is equal to 0, epsilon naught is the energy, and in J is equal to 1 state, the energy of the particle is epsilon 1. So epsilon 0 is the energy of J is equal to 0 state, and epsilon 1 is the energy of the state J is equal to 1. Then we were interested in finding the thermal properties of the system, expressions for the thermal properties of the system of this assembly at some given temperature T. So T is temperature of the assembly, right? So first we discussed the distribution numbers. I will quickly write those expressions and continue with today's lecture. So first we discussed the distribution numbers. Or occupation numbers of the two states. For that, what we did, we first wrote the expression for the partition function as exponential minus epsilon naught over kBt times 1 plus exponential of minus epsilon by kt. We've already discussed this. We named in the previous lectures this equation as 1. So it is the partition function of this assembly. Z is equal to exponential of minus epsilon naught over kBt times 1 plus exponential of minus epsilon over kBt, where epsilon is the energy difference between the energy levels. So it is epsilon 1 minus epsilon naught, right? So then we said it can be thought of as product of two factors, Z0 and ZTH. First factor or term we call the 0 point term, and second factor or term we call the thermal term. Then we found the expression for distribution numbers n0 as n over 1 plus exponential of minus epsilon by kBt, which can be also written as equal to n over ZTH, that is Z thermal. We named this equation in the last lectures as 2a. So this is the distribution number pertaining to ground state. N0 is equal to n over 1 plus exponential of minus epsilon by kt. Kb is the Boltzmann constant, or it can be written as n over Z thermal. Then we wrote the expression for n1, the distribution number pertaining to j is equal to 1 state, and that was this expression. N1 is equal to n exponential of minus epsilon over kBt over Z thermal. We named this expression as 2b. N1 is equal to n times exponential of minus epsilon by kBt over Z thermal, where you know Z thermal is 1 plus exponential of minus epsilon by kBt. So this is our equation 2b. Then in the last lectures, we plotted them and discussed their temperature dependence. We defined the characteristic temperature theta. Then in the last lecture, we talked about the another thermal property, another property of the system, that is our second property, internal energy. Internal energy U. So if we wrote the expression U is equal to n epsilon naught plus n1 epsilon, we named this equation 3. First we wrote it as n naught epsilon naught plus n1 epsilon 1. Then we wrote it as n epsilon naught plus n1 epsilon. Epsilon is the energy difference of the states. We named this equation as equation 3. This is the internal energy of the system or assembly, right? And N1 is given by equation 2a, where N1 is given by not 2a, it is 2b. Equation 2b, right? So this is the internal energy. First term is the zero energy, 0 point energy, the energy of the assembly at T is equal to 0. In the last lecture, we plotted this internal energy as function of temperature, and we saw the transition in the behavior of the assembly around the characteristic temperature theta, right? Now, today we will move to another thermodynamic property of the system, which I label as number 3, that is heat capacity at constant volume, which is denoted as C subscript V. Remember, the heat capacity at constant volume is the amount of energy required to raise the temperature of this assembly through 1 degree Celsius temperature at constant volume, right? When volume is constant, it is understood that the energy levels are constant, because energy levels pertaining to this assembly are dependent on the volume of the system. So it is the heat capacity at constant volume, or you can say heat capacity at constant energy levels. Now, how we find it? Simple. You have to differentiate the internal energy of the assembly with respect to temperature, treating volume as constant. So when you do it, remember your U is given by equation 3, where N1 is to be replaced by the expression in equation 2b. Then when you differentiate it partially with respect to temperature at constant volume or constant energy levels, you get this expression. What is the expression? I will write directly. Cv is equal to N kb. Then I have theta over T square exponential of minus theta over T. Then in the denominator, I have 1 plus exponential of minus theta over T whole square. I name this equation as equation 4, and I give you the home assignment here. I call it home assignment. Check it. What you have to do, you have to differentiate the internal with respect to the temperature. You have to take this expression 3, put N1 from 2b equation, then differentiate U with respect to temperature, treating volume or energy levels as constant. Remember here in this expression, what is our theta? Theta is the characteristic temperature, which by definition is epsilon by kb. Epsilon by kb is our theta. Let me check this expression. Cv is equal to n kb times theta over t whole square times exponential of minus theta by t divided by 1 plus exponential of minus theta over t whole square. Let us plot this result and see how it varies with temperature. So let me plot it and use another color for it. Let me use this green color. So it varies with temperature like this. So on this side I have my CV of the assembly, and on this side I have temperature. So let me plot and draw the figure first. This is 1 theta, then it is 2 theta, then it is 3 theta, right? So here I have temperature as theta. Let me use now another color for the curve. Let me use blue color. So it varies like this. This curve is like this. It increases and attains this maximum. Then it goes down like this. This maximum peak value here is, this maximum value here is 0.44 N kb. This is how this heat capacity at constant volume changes with temperature. It attains maximum, then decreases with temperature, and that maximum value is 0.44 N kb. And you can see that there is a transition in the behavior around the characteristic temperature theta. Now we consider another property, property 4 of this assembly, that is entropy. S. Now how to obtain the entropy of this assembly in question? What we do, we first figure out the Helmholtz free energy of the assembly. Remember the definition of the Helmholtz free energy. Helmholtz free energy is defined as is denoted by F. F is equal to U minus Ts. U is the internal energy, T is the temperature, S is the entropy. So this is thermodynamic definition of Helmholtz free energy, thermodynamic definition. Then what is it? Is statistical definition. Statistical definition. Or you can see how this definition translates when we use statistical physics to express Helmholtz free energy. It turns out to be, let me use here another color. Minus n kb t ln z. This is the statistical definition of Helmholtz free energy. F is equal to minus n kbt ln z. Z is the partition function, T is the absolute temperature, kb is Boltzmann constant, and n is the number of particles in the system. So here I give you another homework. Let me write it. Homework. Do it at home. You take F is equal to U minus Ts, that is thermodynamic definition. Then you have to reach from this definition to this statistical definition and prove that from statistical physics, F is minus n kbt ln z. So what we do for the assembly, we find its free energy from this expression. We put z in this expression. So using equation 1 for z partition function, that's our equation 1. This is our partition function. So we put in this expression and write the expression for the free energy, so Helmholtz free energy. When you do it, it turns out to be equal to n epsilon naught minus n kb t ln of 1 plus exponential of minus epsilon by kt. Let me check it. N epsilon naught minus n kbt ln of 1 plus exponential of minus epsilon by kbt. Again, this first term is the 0-point term. Let me use another color here. So this n epsilon naught is the 0-point term, and second term is the thermal term of the Helmholtz free energy of this assembly. It is thermal term. I name this equation as equation 5. Previous equation was equation 4. Yes. So it's my equation 5. Here you have another home assignment. You have to check it. Check it. Check this at home. How you check it? We use equation 1 for Z partition function, put it here and simplify, you will get equation 5 for F, Helmholtz free energy. Now, how to get, actually we are interested in entropy. So we are taking this route to find entropy. Entropy is obtained by one differentiation of this free energy with temperature. We have an expression, entropy is equal to minus times the derivative of Helmholtz free energy with temperature, treating V and N as constant. N is the number of particles, V is the volume of the system. That in other words means that the number of particles is to be assumed constant. Volume constant means the energy levels are constant. So when you differentiate partially F with T, treating V and N constant, then negative times that derivative gives you entropy. So we take this F from equation 5 and differentiate it with temperature. Then we do negative times of that, we will get this expression. S is equal, I will write directly, you have to check this also. S is equal to NKB ln of 1 plus exponential of minus theta by t, then I have another term plus theta over t exponential of minus theta over t. Then in the denominator I have 1 plus exponential of minus theta over t, then this whole thing is in these curly brackets. So let me name this equation 6. This is your equation 6. Let me check it. It is NKB is outside, NKB times, then inside these curly brackets, I have ln of 1 plus exponential of minus theta by t is the first term. Inside the curly brackets, ln of 1 plus exponential of minus theta by t. Then in the second term, I have plus theta over t exponential minus theta by t in the numerator. In the denominator, I have 1 plus exponential of minus theta over t. So here you have another assignment. Here I will give you 2 assignments. Where is my misses? First, I will change the color of my pen. So one assignment is, check this. That is, you have to check how we obtain S through this equation. Negative times the partial derivative of the t, v and n constant. Then second assignment, you have to check this expression. Check this one. How? You have to use this partial derivative expression for S and use F from equation 5 and solve. You will get equation 6. This is another assignment. Now let us plot this S with T and see its behavior. Let me plot it. So I plot now entropy of this assembly versus temperature. There's be 0 here. This is 1 theta characteristic temperature. This is 2 theta. Then I have 3 theta. So at theta, I draw a line, dotted line on this side. Let me draw curve with another color. I think let me use green. The behavior of entropy is like this. We try to plot it. Goes like this. This is the behavior. This maximum value is the limiting value of S. Here, the value of S is N KB ln 2. N KB ln 2. I think I will try to make this curve a bit neat, or I think it's okay. Okay, it's okay, you can understand it. It is rough. So you can see what is happening here. The behavior is changing around this characteristic temperature theta, and see the high and low temperature behavior compared to theta. When theta is small compared to T, that is in this zone, when T is much less than the characteristic temperature theta, S is frozen out exponentially towards the value 0, which it must attain according to third law of thermodynamics, because we know as T approaches 0, S must approach to 0, which third law of thermodynamics. And you can understand it as T approaches 0, what happens? We have only 2 states in the system, ground state and one upper state. So as T approaches 0, what happens in this assembly? All the particles enter the ground state. That means the assembly becomes completely ordered. That, in other words, means sigma is 1. There is only one microstate corresponding to the assembly, because it is completely ordered assembly when all the particles enter the ground state. And when sigma is 1, you can understand it from this expression, or this expression, S is equal to K B ln sigma. When sigma is 1, ln 1 is 0, so S is 0. This is what happens. Now at high temperatures, the particles are randomized. At high temperatures, the particles are randomized between the two states so that sigma is equal to 2 raised power n, because states available are 2, particles are n. So S reaches the expected value, which is nkb ln 2, which you can see from the figure. Because when we have S is equal to, from this expression, kb ln sigma, when you put for sigma 2 raised power n, you get n kb ln 2, right? Because sigma is 2 raised power n, so log m raised power n is n log m. So you get the value for S as nkb ln 2, which is the maximum value of S to which this curve is approaching. You can get this result from this expression also, equation 6. You can check that as an exercise also. In equation 6, you go to the low temperature zone, that is T much less than theta. You will see S will approach to 0, and high temperature zone, when T is much greater than theta, this expression will give you nkb ln 2. You can check it. This can be another exercise. So you can see how this behavior of this system changes. So this is all for today. Let me summarize this. We have completed this example today, finally. So let me summarize this lecture, what we have done. We have taken this example of an assembly of particles with two states. The particles were localized, weakly interacting, and there were only two single particle states with energies E epsilon naught and epsilon 1. Then we discuss the thermal properties of this assembly at given temperature T. First, we discuss the distribution numbers. We used the ideas which we have learned in the previous lectures. What is the partition function? And in this example, we understood how to write partition function for this assembly, then how to obtain the distribution numbers, how to obtain the internal energy, then how to obtain the heat capacity at constant volume, and how to obtain the entropy of the system. This was our example to illustrate these things. Now I will remind you your assignments. So first assignment I gave you here to check this expression for CV. Then another, prove this f is equal to minus n kbt ln z. Then check how f is obtained using equation 1 for z. So you have to check equation 5, how we obtain it. Then you have to check this s is equal to minus dou f by dou t at constant v and end. And you have to see by differentiating t with respect to t, the free energy in equation 5, treating v and n constant, and negative times of the derivative, you should get equation 6 as the expression for entropy of the system. Then these two limiting cases, when low temperature is low and temperature is high, you should get S is equal to 0 for low temperature when T approaches 0 from equation 6, and when T is very large compared to characteristic temperature theta, you should get S as nkb ln 2. So this is all for today. Go through all the lectures and do all the assignments which I give you during the lectures. And don't forget to like, share, and subscribe my channel. You can have queries. You can comment in the comment box. Thank you very much. Assalamu alaikum.